Hello everyone, welcome to this lecture. In the last lecture we started studying modal parameter estimation methods and we studied a peak picking method. Now in this lecture we are going to study two more methods. The first is circle fit method and then the line fit method. After we study the circle fit method, we will consider a simulated example to identify modal parameters using circle fit method, and then we will consider the basic principle of line fit method, and in the end we will look at what are residuals and how residuals can be approximated. So, let us first of all look at what is circle fit method. The circle fit method utilizes the property that the Nyquist plot of the receptance of a single degree of freedom system with structural damping, it traces a circular arc, right. This we have studied in one of the lectures earlier, right, when we studied the properties of the FRFs, and we also saw that the mobility plot of the receptance of a single degree of freedom system, okay, with structural damping, that also traces a circular arc. So, this is basically the principle of the method, that we can fit a circle to the FRF in the Nyquist plane in order to find the modal parameters. However, the FRF is contributed by more than one modes, and therefore, in the Nyquist plane the FRF will not exactly trace a circle. The circle fit method is also based on single degree of freedom assumption, but this assumption is slightly different than the single degree of freedom assumption in the peak picking method. So, let us look at the basic idea of the method. For a multi degree of freedom system with structural damping, the FRF is contributed by n number of modes, right, if the system is of n degree of freedom, and if we focus our attention on, let us say, rth mode, right, then we can segregate the contribution of the rth mode as indicated by the first term. So, this first term indicates the contribution of the rth mode. And the second term indicates contribution of all the rest of the modes, right, other than the rth mode. So, therefore, if we represent these contributions in this form, so we can write down alpha jk as r c jk. So, r c jk represents the contribution of the rth mode, right, and then plus r b jk. So, r b jk represents the contribution of all the other modes. Now, here r c jk is like the FRF of a single degree of freedom system, and therefore, it will trace a circular arc in the Nyquist plane, and RBJK is the contribution of all the other modes to the FRF. Now, if we focus our attention on a narrow frequency band around Rth peak, then in this band the contribution RBJK will be very small, right, and the contribution of RCJK will be dominant. And if we assume that RBJK is constant, right, which is what the circle fit method assumes, that the contribution RBJK is constant in this small frequency band, then the circular trace of the RCJK term will be only translated in the Nyquist plane, okay, and therefore, the circular nature of the this single degree of freedom FRF due to Rth mode will not be distorted if RBJK is constant. So, if that is so, then alpha jk will also trace a circular arc in the Nyquist plane in the narrow frequency band around Rth peak. So, this is the idea behind the circle fit method. So, therefore, if RBJK is constant in a band around the Rth peak, then the plot of alpha jk over the frequency band would also trace a circular arc in the Nyquist plane. So, for a typical system, you can see plots of RCJK, RBJK and alpha jk are shown. So, RCJK is supposed to be a perfect circle or perfect circular arc as we see from here. Now, RBJK, which is the contribution of all the modes other than the Rth mode, we see that the contribution is not large in the narrow frequency band, right, and then therefore, the alpha jk, the plot of alpha jk in the Nyquist plane also almost looks like a circular arc, right, that is the deviation from the circular arc is very small because RBJK is small in the narrow frequency range. So, this means that we can therefore fit a circular arc to the measured FRF alpha jk and then determine the modal parameters from that circle. Okay. So, this is the idea behind the circle fit method. So, let us see how we can perform fitting of the circle to the FRF. The FRF is in general complex. So, it has real part and imaginary part. Okay. So, let us represent the real part of the FRF by variable x and the imaginary part of the FRX by variable y. So, x and y are the real and imaginary parts of the FRF. Now, the equation of circle, we know that it is given by x minus xc whole square plus y minus yc whole square is equal to r square. So, xc, yc are basically the coordinates of the center of the circle and r is the radius of the circle. And if we can also express this equation in this form, that is x square plus y square plus ax plus by plus c is equal to 0, right. So, here the coefficients a, b, c, they are related to the coordinates of the center and the radius of the circle, and they are related by these relationships, right. So, therefore, if we can determine the coefficients a, b, c after fitting the circle, then we can determine the coordinates of the center and the radius of the circle using these relationships. Now, to fit the circle to the FRF in the narrow frequency band around rth peak, we will have some discrete frequency points in that band, okay, and the FRF would be known at all those points. So, therefore, we define an error function, right, which defines the error in the fit. So, here a, b and c coefficients are unknown, and if we now substitute for a particular frequency point, let us say ith frequency point, the FRF value x and y, if they are substituted in the equation of circle, then the left hand side of the equation basically represents the error, right. So, you can see if I substitute x I and y I corresponding to the frequency omega I, if I substitute in this equation, then the left hand side, the magnitude of left hand side essentially represents the error in the fit. So, ideally we want that if the fit is perfect, this left hand side should be 0, right, because then only it will satisfy the equation of circle, right. So, if there are now m number of frequency points, so here you can see this is m is the number of frequency points. So, we can sum the error over all the m points, that gives us the total error. So, this is nothing but the total error in the fit, total error in the fit, and now we would like to minimize this error, okay. So, we would like to choose values of a, b, c such that e is minimum. If there is perfect fit, the error will become 0. However, if the fit is not perfect, there will be some non-zero error e, but then we like that e should be as small as possible. So, for e to be small, we need to satisfy the conditions that the first derivative of e with respect to a, b, c, the unknowns, should be 0. So, when these conditions are applied, it leads to 3 equations, and those 3 equations we have put into matrix form as shown here. Coefficient matrix on the left hand side and a vector on the right hand side of this equation, they depend on the FRF values xi and yi and the number of frequency points m. Now, we can set this equation based on the measured FRF in the narrow frequency band, and then we can solve these equations, right, to find the unknowns a, b, c. So, essentially there are 3 equations and 3 unknowns, okay, and therefore, we can solve for a, b, c. So, once we solve for a, b, c, then we can find the coordinates of the center of the circle and the radius of the circle, right. So, now once we have fitted the circle and found the center of the circle and radius, how do we find the modal parameters? So, from the equation of the circle, we see that the modal parameters are related by a nonlinear relationship to the center coordinates and the radius of the circle. So, therefore, a simpler procedure has been proposed to find the modal parameters, that is natural frequency, loss factor and modal constant from this circle that has been fitted. So, how is natural frequency is estimated? So, it is based on the concept of the maximum sweep rate which was proposed by Kennedy and Pankow long back. This sweep rate is the rate of change of angle subtended at the center of the circle with frequency. So, let us try to analyze that how this sweep rate is related with the natural frequency. So, we have looked at this RCJK expression, which is the FRF contribution due to Rth mode. So, now we know that the contribution of other modes RBJK, it only translates the RCJK, right, in order to produce alpha JK. So, whether we use alpha JK for the analysis of sweep rate or we use RCJK for the analysis of sweep rate, it should not make a difference, because the circular arc remains circular arc due to the translation induced by the term RBJK, right. So, therefore, we will now use RCJK expression in order to see that how the sweep rate is related with the natural frequency. Further, we also note that RCJK can be written as product of RAJK and RCUJK. So, this RCUJK is nothing but 1 upon omega r square minus omega square plus I eta r omega r square. So, it is based on unit modal constant because its numerator is unity. So, RCUJK corresponds to single degree of freedom phi with unit modal constant, and that is why the superscript u has been placed and to indicate that it is based on the unit modal constant. What is the role of RAJK here? The RAJK in general is complex. The modal constant will be complex and therefore, it will have magnitude and its phase. So, the magnitude of the modal constant will essentially change the diameter of the modal circle corresponding to RCUJK in order to produce the diameter of the modal circle represented by RCJK, right. And the phase of RAJK, it will rotate the modal circle represented by RCUJK. Okay. So, effectively the effect of modal constant RAJK is to change the diameter of the unit modal circle and rotate it in the Nyquist plane in order to produce the modal circle or the FRF represented by RCJK. Okay. And therefore, because circular nature is still preserved in these operations, and that is why the analysis of sweep rate can also be carried out based on the unit modal circle represented by RCUJK. So, therefore, the trace generated by RCUJK is also a circular arc and is referred to as unit modal circle since it is based on a unit modal constant. So, this shows the plot of RCUJK, that is the unit modal circle. So, it is based on unit modal constant. So, here this point A corresponds to frequency omega is equal to omega r, right. So, we should note that different points on this circle, they represent different frequencies. Okay. So, these are all the different frequency points like this here. They are all different frequency points on the circle, and the point A corresponds to the frequency point where omega is equal to omega r, because we can see from the expression for RCUJK that the real part of RCUJK is 0 at omega is equal to omega r, right, and that is why this omega to omega r corresponds to point A, and this point B corresponds to some frequency omega. Okay. So, this angle theta you can see is the angle subtended by this arc AB at the center, right, and beta angle has been also shown here. So, now we can write down based on the coordinates of point B expression for tan beta. So, tan beta is given by the imaginary part of RCUJK divided by the real part of RCUJK, right. It is clear from the trigonometry. And therefore, what we get relationship tan beta is equal to eta r omega r square upon omega r square minus omega square. From the geometry we can also write down the relationship between theta and beta, and theta is nothing but twice of pi by 2 minus beta, right. So, now what we can do, we can substitute value of beta from this equation in the expression for tan beta. So, it leads to this equation that omega square is equal to omega r square minus eta r omega r square tan theta by 2, right, and then we can find the sweep rate, which is the derivative of theta with respect to omega square. So, then we can from this expression determine d theta by d omega square, which turns out to be minus 2 eta r omega square divided by omega r square minus omega square whole square plus eta r omega r square whole square. And what we note from here that this quantity d theta by d omega square, it is maximum when omega is equal to omega r, is not it, because the denominator takes the minimum value, right, when omega is equal to omega r, and that is why the quantity d theta by d omega square will be maximum. So, therefore, we say that the sweep rate would be maximum when omega is equal to omega r, right, and this fact is used to locate the natural frequency, because the question would be that when there are several frequencies in the narrow frequency band we have taken for the analysis and where the circle has been fitted, which frequency corresponds to the natural frequency. So, now that frequency can be located based on the concept of sweep rate. So, we can find now the sweep rate for different pairs of points. So, we would take a particular pair of point and then we will try to find what is the angle subtended by that pair at the center of the circle using the trigonometry, and then that we do for all pairs of points. So, the pair of point for which the angle subtended at the center is maximum, that pair corresponds to the pair with maximum sweep rate, and then the average of those frequencies forming the pair can be taken as the estimate of the natural frequency. So, this is the idea behind locating the natural frequency based on the maximum sweep rate and once the circle has been fitted. Now, how we determine the loss factor? So, for the loss factor we can see that this relationship we derived just now, that tan theta by 2 is equal to omega r square minus omega square divided by eta r omega r square, right. This expression we have derived. And then from this relationship then we can write down equation corresponding to omega a and omega b. So, in these equations theta and theta b are the angles subtended by the arcs formed by the frequency points omega a and omega r and omega b and omega r. So, these arcs what angle they subtend at the center are nothing but angles theta and theta b. Okay. So, therefore, how we can now find the sweep the modal loss factor? By solving these two equations we get this expression for eta r, which is equal to omega a square minus omega b square divided by omega r square into bracket tan theta by a by 2 plus tan theta b by 2. So, if we have chosen the frequency points omega and omega b, and if we can determine the angles theta and theta b from the circle that has been fitted, then using this expression we can find the modal loss factor eta r. Now, how we estimate the modal constant? So, we have seen this relationship, right, on the previous slides, that r c j k is equal to r a j k, which is the modal constant, multiplied by r c u j k, is not it? And at omega to omega r we can simply write r c j k at omega r is equal to r a j k into r c u j k at omega r. Now, in general left hand side and right hand side in this equation are complex quantities. So, this means that the magnitude of the left hand side should be equal to magnitude of the right hand side, and the phase of the left hand side should be equal to the phase angle of the right hand side. So, let us first of all look at the condition that the magnitude of the left hand side is equal to magnitude of the right hand side. So, magnitude of r c j k should be equal to the magnitude of r a j k into magnitude of r c u j k, both evaluated at omega r. Now, what is the magnitude of r c j k at omega r? Because r c j k omega r is nothing but the circle that has been fitted, right, and therefore, the magnitude of r c j k at omega r will be equal to the diameter of the circle, okay, and that is why this is nothing but equal to 2 r. What is magnitude of r c u j k omega r? That we can easily determine from the equation, right. So, we saw that it is completely imaginary, the real part is 0 of r c u j k at omega r, right, and that is given by 1 upon eta r square into omega r square. So, if we substitute therefore these values in this equation, so what we get 2 r is equal to magnitude of r a j k into 1 upon eta r omega r square, right, and therefore, from here we get the magnitude of the modal constant as 2 r into eta r into omega r square. Now, because we have fitted the circle, we know the radius of the circle, and since we have already estimated the natural frequency and modal loss factor, the omega r and eta r they are also known, and therefore, from this relationship we can determine the magnitude of the modal constant. Similarly, the phase of the left hand side should be equal to the phase of the right hand side, and based on this observation we can write down the phase of the modal constant r a j k equal to the phase of the r c j k at omega r minus phase of the r c u j k at omega r. Now, what is the phase of the r c u j k? The phase of the r c u j k, let us say if you measure from the negative imaginary axis, then the phase of this is 0, right, because it is symmetric with the negative imaginary axis. So, therefore, the phase of the modal constant r a j k is nothing but equal to the phase of the r c j k at omega r, right. So, therefore, how we can determine that phase? We can determine by finding the phase angle of r c j k at omega r measured from the negative imaginary axis. So, in this way we get the magnitude and phase of the modal constant. So, let us now take an example to identify modal parameters using circle fit method, and we are going to consider and use simulated data for this modal parameter estimation. Let us take this cantilever structure which we also used in the case of peak picking method, right, and let us say we have measured a row of the FRF matrix, okay, and there are 5 test points on the structure, and no FRF along the translational DOF at these 5 test points have been measured. So, let us focus our attention on analyzing the third peak in the transfer receptance alpha 1 phi, okay. Let us try to analyze third peak in this transfer receptance. So, you can see this is the plot of the receptance alpha 1 phi that has been shown here, the Nyquist plot. So, on the x axis the real part of the FRF is plotted, on the y axis we have the imaginary part. So, it is a plot of real part and imaginary part of the receptance. So, what we see, there are 4 loops that are appearing here. So, these 4 loops correspond to the 4 resonances which are there in the 0 to 400 hertz frequency range of the receptance. So, each loop corresponds to a mode of vibration. So, now our first step is to feed the circle, right. So, for that we select a narrow frequency band around the third peak. So, you can see this is the zoomed view of the third resonant peak that is shown here, okay. And then we select a narrow frequency band. You can see this is the frequency band we have chosen, right, around the third resonant peak. Let us look at the Nyquist plot of the FRF in this narrow frequency band. So, this is the Nyquist plot. So, there are 21 frequency points in this narrow frequency band, right, and the band starts from 170 hertz and it ends at 175 hertz, and we can see these are this is the Nyquist plot and with all the frequency points being shown. So, there are now 21 discrete frequency points, and now we have to fit circle to this, and we have studied how to fit the circle, because at all these frequency points we know the FRF values. Then we can set up the coefficient matrix on the left hand side and a vector on the right hand side, and then find the coefficients A, B, C by solving those equations. So, once that is done, we get the circle, and then we can find the radius of the circle and the coordinates of the center of the circle. So, this is the fitted circle, right, and these are the coordinates of the center of the circle and the radius of the circle. So, now what we do, we find now the angle swept by a pair of frequency points. So, therefore, we choose, for example, let us say this pair, this is one frequency, another this second frequency, and then from the center of the circle we determine, let us say if the center is here, then we determine the angle swept. So, this is the angle that is swept by this pair of frequency point. So, this we determine because we know the coordinates of the center, we know the coordinates of these frequency points in the Nyquist plane, because the FRF values are known, and then we can determine this angle, and this we repeat for every successive pair of frequency point, right, and then we compare all those subtended angles, and a pair for which the angle is maximum, that pair corresponds to the pair with maximum sweep rate, and then we can find the natural frequency by taking the average of the frequencies making up that pair, and that frequency is found to be 172.9 hertz. So, in radians per second it should be 2 pi 172.9 radians per second. So, in this way we get the estimate of the natural frequency for the third peak. Now we find a modal loss factor, for which now we select 2 frequency points, one on either side of the frequency omega r. So, you can see here we have chosen 2 points. You can see this is the first frequency, this is another frequency, and this is the natural frequency, right, which is the omega r. So, one on either side we have chosen, and now we find what are the subtended angles, these angles. So, these are the nothing but angles theta A and theta B, which appear in the equation for finding the loss factor. And then these are the frequencies 171.5 hertz and 174 hertz, these are the frequency points omega and omega b, and then we find these angles theta A and theta B which are subtended at the center, and then we find the value of the modal loss factor which is found to be 0.0159. Now we find a modal constant. So, first we will find the magnitude and then the phase of the modal constant. So, we know the expression for the magnitude of the modal constant, which is 2r eta 3 omega 3 square, and the modal constant which we will obtain will be 3a15, because it is the peak 3 and the FRF is transfer receptance alpha 1 phi. So, therefore, we get the magnitude of the modal constant, because we know the radius of the circle and we also know the modal loss factor and the natural frequency for the third peak. Similarly, we find the phase of the modal constant. So, we find a phase, right, the angle of the line joining the center with the point omega 3, okay, with the negative imaginary axis. So, that angle of that line, right, that radial line formed by the center of the circle that has been fitted and frequency point omega 3 on the circumference of the circle, that line, the angle of that line with the negative imaginary axis, that angle we can find out from trigonometry. So, that angle is nothing but the phase of the modal constant, and that phase turns out to be minus 7.82 degree. Okay. So, in this way we get the magnitude and the phase of the modal constant, and thus the modal constant becomes known. So, now what we do, we analyze this third peak in the other FRFs, okay, we analyze the third peak in the other FRFs. So, that gives us now the natural frequency, modal loss factor and modal constant for those FRFs. The average values of natural frequency and a modal loss factor can be found, right, because we want to have a single consistent estimate of these quantities, right, and they are supposed to be constant for all the FRF, right. So, we can take the average and that can be treated as a consistent estimate of the natural frequency and modal loss factor. And then once we have the modal constants for all the FRFs, then we can determine the mode shape for the mode 3 by following the procedure which we learned when we discussed peak picking method. From the modal constants we can determine the mode shape. And then this procedure then we repeat for the other peaks in the FRF, right, and in this way then we get the model corresponding to the frequency range of measurement. Let us now look at the line fit method. So, line fit method essentially fits a straight line to the inverse of an FRF, okay, and hence it is also called inverse FRF method. So, if you take reciprocal of an FRF, then we can show that this FRF can be approximated by a straight line in a narrow frequency band around a resonance peak, and that is the principle of the method. Okay. The reciprocal of the FRF has the units of dynamic stiffness, and that is why this method is also referred as dynamic stiffness method. So, this method is fitting the data in the frequency domain, so it is a frequency domain method, and it also is based on the single degree of freedom assumption. So, let us look at the basic principle of the method. So, we know that the FRF of a multi degree of freedom system with structural damping, it can be written as the sum of the FRF contribution of the Rth mode and the contribution of all the rest of the modes. Here the first term is the contribution of the Rth mode, and this is the contribution of all the other modes. So, the line fit method assumes that this contribution RBJK is negligible in a narrow frequency band around the Rth peak, and in that narrow frequency band the contribution of the Rth mode is dominant, right, and the RBJK is negligible. Therefore, we can approximate the expression for the alpha jk in a narrow frequency band around the Rth peak by the FRF of the single degree of freedom system corresponding to the Rth peak. Now, if you take the reciprocal of this FRF, then it is represented by ZJK, right. So, you can see this ZJK is the reciprocal of alpha jk. So, this ZJK is essentially given by omega r square minus omega square plus I eta r omega r square divided by RAJK. We see that the expression on the right hand side is a linear function of omega square, right. So, it means ZJK and omega square they can be approximated by a straight line relationship. The modal constant RAJK is complex, right. So, let us write it in the form of C plus ID, and if you substitute this in this expression for ZJK and simplify this expression separating the real and imaginary parts, then we can write down the expression for ZJK in the form of real part ZR plus I times the imaginary part ZI, right. And then we can also see that ZR is nothing but real part of ZJK, and it is given by omega r square minus omega square into C plus eta r omega r square d divided by C square plus d square. And we see that this right hand side is a linear function of omega square. So, we can say that the ZR and omega square they are linearly related, right, and therefore, we can write this expression in this form. We can say that ZR is equal to mr omega square plus QR. So, mr and QR are the intercept and slope respectively of the line between ZR and omega square. Similarly, the expression for ZI we obtained, and we see that the right hand side of this expression is a linear function of omega square, and therefore, this relationship of ZI and omega square can also be represented by a straight line relationship, right, as ZI is equal to mi omega square plus Qi. So, here again mi and Qi are the slope and intercept respectively of the line between ZI and omega square. Let us now look at the plot of ZR and FRF for a typical system to see that what is their nature in a narrow frequency band around different peaks. So, you can see these are the plots. So, the first plot here is the plot of the FRF, dB value of the FRF plotted on the y axis as a function of omega square. So, the frequency axis is here not omega, but omega square. There are resonant frequencies appearing in this plot, right. And then the second plot is the plot of the real part of the inverse FRF, that is nothing but plot of the ZR, right, as a function of omega square. And then the third plot is plot of the imaginary part of the inverse FRF, which is plot of the ZI. Let us focus our attention on a frequency band around this peak 3, right. So, what we see in this narrow frequency band, this plot of ZR versus omega square is almost like a straight line. Similarly, the plot of ZI versus omega square is again almost like a straight line in this frequency band. Similarly, if we look at a narrow frequency band around, let us say, the second peak, the same thing can be said, right, in this range. So, this plot of ZR versus omega square and ZI versus omega square is again approximated as straight lines in these regions. So, this is the principle of the line fit method, okay, that in narrow frequency band around the resonant peaks, the plot of verse FRFs, they can be approximated as straight lines, and then from those fits then we can infer the values of we can determine the values of modal constants. So, what is the idea? Therefore, we for a given FRF we find the reciprocal of the FRF, then find the real part of it, right, we plot the real part versus omega square, and then we choose a narrow frequency band around a particular peak which we are analyzing, and then we fit the straight line to those points in that narrow frequency band, right, and then we get the relationship between ZR and omega square. So, when we feed the straight line, we get the slope and intercept of that line, and similarly we do this for the imaginary part of the inverse FRF, and from that we get the slope and intercept mi and qi of the line. And then what we do? We determine the modal parameters omega r, eta r, c and d, which make up the modal constant for the Rth mode using these relationships. So, from the relationships or the expressions we derived earlier, we can derive and obtain these relationships for modal loss factor, natural frequency and c and d. So, in this way we get the modal parameters by fitting straight lines to the real and imaginary part of the inverse FRF. Now, we are going to discuss what are residuals. The residuals are nothing but the contribution of the modes outside the frequency band, and then we saw that in the single degree of freedom methods the residual contribution is either neglected like in the peak peaking method and the line fit method, or is approximated as a constant like in the circle fit method. So, the residual contribution, right, of the modes which are outside the frequency band that has been chosen for analysis, those contributions are either completely neglected or they are assumed to be constant. However, the problem is that if the residual contribution is neglected, then that contribution is attributed to the modes in the analysis frequency band, and this adversely affects the accuracy of the estimated model parameters. So, when we neglect the residual contribution, we are attributing the contribution of all the modes only to the modes which are inside the frequency band, okay, and this distorts the fit, and which basically affects the accuracy of the model parameters that are estimated. So, let us first of all look at what is the nature of the residual contribution, and then how this residual contributions can be approximated for model parameter estimation. So, let us look at first of all what is the nature of the residual contribution. So, the FRF for a multi-degree of freedom system with structural damping is given by this expression, right, which shows that the FRF is contributed by the n modes of the system if the degree of freedom of the system is n. So, let us say if we are focusing our attention on identifying modes m1 to m2, right, we are focusing our attention on a frequency range which contain modes from m1 to m2, then we can represent the FRF contributions as sum of three terms. The first term here you can see, this first term is the contribution of modes 1 to m1 minus 1. This second term makes the contribution of, shows the contribution of modes from m1 to m2, and the third term shows the contribution of the modes from m2 plus 1 to n, isn't it? And then we can represent these contributions in this form. So, alpha jk can be written as alpha jkl plus alpha jk band and alpha jkh. So, the modes which are on the lower side of the band we are analyzing, right. So, the band we are analyzing is M1 to M2. So, the modes which are on the lower side of this band, their contribution is referred or called as low frequency residual. Okay. So, this is the low frequency residual, and then the contribution of the modes which are on the higher side of the band we are analyzing, right, which is this contribution is referred as high frequency residual, and the contribution of the modes from M1 to M2 is referred as alpha JK band here. Let us take a typical case and see how these low frequency and high frequency residuals look like. So, for a typical system, here you can see we have plotted the alpha JK band and alpha JK. So, if you look at the first figure, we have plotted the contribution of the modes inside the band shown by yellow line, right. So, you can see this is the alpha JK band and this is being shown by this yellow line. So, it shows the contribution of the modes inside the band, and then dotted line shows the complete FRF taking into account contribution of all the modes. So, if you look at the band which you have chosen, this is the band we have chosen, right. So, in this band when we do the curve fitting by neglecting the contribution of the modes which are outside this band, then we are essentially forcing the fit of this yellow curve onto the dotted line curve, right. We are forcing the fit of alpha JK band, contribution of the modes in the band to the contribution of all the modes in this band represented by the dotted curve, and this obviously will distort the fit and lead to inaccuracies in the model parameters that are estimated. This second figure shows the plot of low frequency residual, right, and plot of the all the modes which are on the lower side of the band. Okay. And the third figure shows the plot of the high frequency residual, that is the plot of contribution of modes which are on the higher side of the band. So, what we see, the low frequency residual in the frequency band, it can be approximated as the mass line of the receptance of an SDF system. So, although the modes which contribute to low frequency residual they are more than one, and therefore, their contribution cannot strictly be represented by a single degree of freedom system, right, but still we can approximate this contribution by mass line of the receptance of an SDF system. So, we can write therefore alpha JKL approximately as minus 1 upon m JK omega square. So, this m JK represents the fictitious mass of the corresponding to the mass line. Similarly, the high frequency residual in the frequency band can be approximated as the stiffness line of the receptance of an SDF system. Okay. So, we can see from the plot that the contribution of the high frequency residual in the frequency band we have chosen, it looks like a stiffness line, right, it is like a horizontal line. So, KJK is the hypothetical stiffness of the stiffness line. Therefore, with these approximations we can write the FRF expression as alpha JK is equal to first the low frequency residual, which is minus 1 upon m JK omega square, and then the contribution of the modes M1 to M2, and then we have the high frequency residual which is 1 upon KJK. So, therefore, here we see that the MJK and KJK are also now two additional unknowns which need to be determined during curve fitting, right. So, in addition to finding the model parameters of the modes from M1 to M2, we also need to determine these coefficients of the low and high frequency residuals. So, the residuals can also be modeled as pseudo modes. For example, for the low frequency residual we can assume a fictitious pseudo mode which is making that low frequency contribution, and that can be approximated as 1 upon KJK minus MJK omega square. So, for the high frequency residual also we can have another pseudo mode again whose contribution will be represented by 1 upon KJK minus MJK omega square. So, therefore, we have now two unknowns for each pseudo mode. So, if we are using one pseudo mode for low frequency residual and one pseudo mode for high frequency residual, then we will have 4 additional unknowns which need to determine to model the residual contributions. So, what is the advantage of incorporating the residuals in the model parameter estimation? By incorporating residuals we obtain a more accurate estimate of the model parameters, and therefore, the model we obtain is a more accurate representation of the structure, right. So, for example, we are using model for predicting the response to unknown forces, then the prediction of those responses will be then more accurate. So, in this way today we studied the model parameter estimations using circle fit method and line fit method. We also studied the concept of residuals and how the residuals can be approximated. Now we stop here. Thank you.